Yeah, folks, welcome to this week's KDD2 lecture podcast. We are starting off a new lecture, a new topic. After finishing the stream data mining stuff, we are now looking into sequential data, mining sequential data. And here is the outlook for this and next week. We'll talk about, introduction of to sequential data and similarity models for sequential data this week. And next week we will have a look at time series data, and the week after we'll have a look at spatial temporal data. So the podcast will be, or the duration of the next 3 weeks, including this week, will be a little bit shorter than the usual 2 hours and something. But I hope you appreciate that it's not so dense those weeks here. Okay, so we start off with the introduction to sequential data. So far we mostly dealt with relational data, structured data, flat data from relational tables. And those data sets typically provide a snapshot of some application data at a particular point in time. And of course, we had the data stream environment in the last subsection, in the last lectures, where the data can be updated, and also the patterns can be updated. The patterns can change, so we can somehow see some temporal aspects. But very often we do not have real data stream environments. But still the world is a little different than just this snapshot thing. So we had batch and stream, and there's something which is more or less batch. We have no streaming environment where the stream is endless, but we have some batch scenario, but we still want to gain some temporal insights, or at least some insights into the dynamics of data. So just looking at batch snapshots typically cannot reveal important insights into the dynamics of some application, or in the dynamics of the data behind that application. So in that case, we need to look at sequences of snapshots, for example, to analyze how patterns are changing, evolving, quite similar to data streams, but once again, it's not data streams anymore. We have batches of snapshots of and a sequence of snapshots of the data. So we don't have this constraints about storage limitations and runtime limitations, but we still want to have insights into evolving patterns, changing patterns, and stuff like that. We want to know if certain patterns appear over the sequence in a kind of periodical fashion, so sequential patterns. If there are sequential patterns, what kind of sequential patterns are there? So we can somehow learn something about, again, the dynamics or the changing of data over several snapshots. But once again, not in a streaming environment, but somehow in a batch environment. And in that case, we are talking about sequence data. So sequence data typically allows to measure phenomena or monitor phenomena data over time. Then we're talking about time series, or more generally speaking, in a given order. Measuring or monitoring data or phenomena in a given order of sequential events, and that does not require a concrete notion of time. So in that case, it's general sequence data. If we're talking about the time, if the sequence or the order of the snapshots is in relationship to time, we are typically talking about time series. So sequence is the more general, or sequence data is the more general term, and time series data is usually used if the time is involved and not some general sequence or sequential events. And here are some examples. So for sequence data, we may, for example, look at the sequence of purchases, maybe over time, but not necessarily over time. Sequential pattern could be customers buying A are likely also to buy B within the next 4 transactions. So transaction is a kind of time notion, but it's not really coupled with time. So it's just transactions. Yeah, so we have a sequence of transactions, of purchases, no matter when or how much time elapsed between those purchases, between those transactions, and we potentially want to know things like buying A involves also buying B within the next X transaction or something like that. And in time series data, this is a little different because then we have some data over time. So for example, stock rates over time, and then for example, a potential pattern could be, temporal pattern could be find stocks with similar behavior over the entire time frame or in sub-interval of the time. Because people may hope that if stocks behave similar, we may have a chance to forecast the behavior of stocks. But forecasting stocks is, as you can imagine, from data-driven forecast of stocks is just from the stock data is probably a little naive, as you can imagine. Anyway, so here is the general definition, so to say, or formalization of sequence data. So a sequence, typically denoted by S, has n values, and so the sequence is a mapping of the index set from 1 to n into a domain of values, and this is denoted by O here. So S is a mapping from the index set to the domain here. And then just some terminology here. The set of all sequences of length n is O to the power of n over this domain, of course, the same like here. And the set of all sequences over the domain O is O to the O star. Yeah. So in this set, we are talking about different n's here, or all possible n's, so to say. Yeah. Could be also empty sequences here, of course. I think you know this terminology from other lectures. Yeah, and the sequences can be classified by their domain. So if the domain includes or is made up from categorical values, or if it is made up from continuous values like real numbers or stuff like that. Yeah, so depending on the domain of O, being categorical or continuous, we can do different things with it. Same with just pure relational flat data, as you may remember from KDD 1. Yeah, and here are some examples which fits with the corresponding fit to our terminology here. So, for example, text data are typically some sequences over some alphabet. And here is the alphabet of the letters and the numbers. So and maybe some more like Sonderzeichen and stuff like that. Yeah. So video data is typically some sequences over the set of images, whatever images the domain of images is. Music data can be, for example, be a sequence of notes. Yeah. So the domain here are notes, whatever. Nodes are protein sequences, are typically sequences over the amino acid domain. Yeah, gene sequence is very popular in bioinformatics. You have these nucleotides, CGAT. Each of these letters typically stand for one specific nucleotide, and gene sequences are made of those 4 nucleotides in some given order. So gene sequences are sequences over this 4-letter alphabet in that case, representing the different nucleotides. Yeah, so anyway, and yeah, time series are of course special types of sequences. So any time of any kind of time series are of course special types of sequences. And you probably know a lot like heart rates or stuff like that. So they are special types of sequence data. Yeah, and now, as I said before, the question is how to analyze this. So this will be the next podcast taking care about how to deal with sequence data and or how to mine sequence data. Well, typically what you do with sequence data is first of all you try to map this special representation to your data mining algorithms that you are used to, which typically work on distance measures or similarity measures. So a very, very common approach to deal with sequence data is to define similarity model, similarity or distance function for your sequence data. And we will talk about this in the remaining podcast for this week. So stay tuned.